Okay, let's look at our first example of using this derivative definition. So for the first example, we're going to work with f of x equal to x to the third, the cubic function. And so for part A, we're just going to find, what is the derivative of this function. And let me emphasize that we're taking the derivative with respect to x. And that phrase, with respect to, you'll hear that a lot. And if you see W period, R period, T period, that is the abbreviation for that. Okay, so let's use, we're just going to go straight from the definition. So just straight from the limit definition. So if our f of x is x to the third, so in order to compute this difference quotient part, we're going to have to evaluate the function at x plus h. And so let's see, that's just going to be the limit as h goes to 0. And the f of x plus h part, that's, just x plus h in parentheses to the third power. And then minus the f of x, well, that's just minus x to the third. And then all over h. Okay, so from here, we're going to need to use the binomial theorem, because we've got that binomial x plus h and we need to raise it to the third power. So just as an aside, you may remember Pascal's triangle. Let's see, we have 1, and then you have 1s down the diagonal. And let's see, so let's just do one more level. Well, we're going to go 2 more levels actually. And so to get this number in between here, that's going to be the sum of the two sort of up above it, but you're going to have one to the left and one to the right. So the sum of 1 plus 1 is 2. All right, well, let's do another level because that may not make sense to you. So let's see. You still got 1s down the diagonal. And 1 plus 2, well, that's 3. And then 2 plus 1, that's 3. And, well, we'll do one more level. So 1's down the diagonal. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Okay, so why do we care about Pascal's triangle? Well, let me, just a second, let me erase my dots here now that we sort of know what those numbers mean. And so I'm just going to box in the row that we need, because these are the numbers that are going to show up when we expand this binomial. When we expand x plus h to the third power, we're going to need to know those numbers in that row. Because, okay, well, let's just see. All right, so the expanded form is given here. And so the first thing we need to mention is that, when you get these terms, when you're going from left to right, you're going to have an x to the third, an x to the second, an x to the first power, and an x to the 0 power. Now, that's from left to right. From right to left, notice that we have an h to the third. Whoops, wrong thing there. We have an h to the third, h to the second, h to the first, and then h to the 0. And let me undo all that. So again, from left to right, we have x to the third, x to the second, x to the first, x to the 0. And then from right to left, we have h to the third, h to the second, h to the first, and then h to the 0 would be this term here, where h to the 0, that's just 1. Okay, so that's sort of the pattern that we need to get the terms. And then, well, okay, you can see where the numbers come in here because, well, there's the 1 there. That's this 1. And then the 3. This 3, well, that's this number here. And similarly, this 3 is that one. And then the last one, well, that's here. Right, so that's where those numbers from that Pascal's triangle, that's how they help us. Okay, well, now let me erase all that. So hopefully you've got a good idea, just a good review. Well, okay, there we go. A good review of the binomial theorem. Okay, and so if we had x plus h to the fourth power, and I wouldn't do you that bad on the test, I promise. In fact, probably the most I do on the test might be squared, and we pretty much know how to do that. But just so that you know, if you wanted to expand this binomial x plus h to the fourth power, well, you'd have, you know, from left to right, you'd have x to the fourth, x to the third, all the way down, and then all the way to the right, and then go from right to left, you'd have h to the fourth, h to the third, and so forth. And then the numbers, the multipliers, well, you get those from Pascal's triangle, that next row there. Okay, well, enough of that. No more digressing. Let's get back to the problem. Okay, so we expanded that binomial, so here's where we are. We expanded that binomial. We still have minus x to the third, and then all over h. Okay, so here we are. Well, obviously the next step's going to be the x to the third minus x to the third, right? That's gone. And so from here, if we look at what's left, this part is what's left, and there is an h common to all three of those terms. Now, why is that important? Well, because, you know, we're trying to get rid of this h in the denominator. This h in the denominator is what's causing all the problems, because we can't just plug in h equals 0 because we get 0 over 0. So we've got to remember, when you have the form 0 over 0, that's a clue to try, factor, and cancel. And that's about what we're about to do. So we're going to pull out that h, that common h right there, and we have the 3x squared, you know, this part left. And then finally we can cancel out that h on top and bottom that was causing all the problems. And so that gets us, we've done there. And so now we're at this step. And so we're taking the limit as h goes to 0 of this, what's left. And now we can just plug in h equals 0. And so this part is gone, that's 0, and this is 0. So what we have left is just 3x squared. So, in summary, remember our original is f of x is x to the third. And the derivative of that is f prime, and f prime of x is 3x squared. So in summary, the function is f of x is x to the third, and its derivative, which is read, I'm sorry I didn't say this already, but that's read f prime. Well, I may have said it, but I didn't write it down. That's f prime of x. F prime of x is, that's the first derivative. And so the first derivative of x to the third, we've just shown, is 3x squared. Okay, and so remember that in the definition, what the derivative is going to tell us about is the slope of tangent lines. And so that's going to show up in part B. So part B says, you know, what is the equation of the tangent line to the curve, well, our y equal x to the third, at the point -1, -1. And if you just spend a little bit of time there, you can convince yourself that the point -1, -1 is in fact on that curve. Well, let's look at a picture. So let me draw your attention first. I'll blow it up a little bit if I can do this. So here's our picture. And if you remember from algebra class, the curve y equal x to the third, that's sort of the paperclip function, if you will. It's sort of like you've taken a paperclip and bended it, you know, one way. And that function x to the third is symmetric about the origin. Now, what do we mean by that? Well, so if you take this curve and you rotate it 180 degrees about the origin, so around the origin, rotate it 180 degrees, you'll get the same thing, what you started with. You know, so if you take any point, in particular, if you take the point 1, 1, rotate it 180 degrees, you're going to land at another point that's on the original curve. So that's what we mean by symmetry about the origin. And that is a property possessed by this curve. Okay, so that's just something to know. But our problem here, though, is to figure out the equation of this tangent line. So here is the point -1, -1. So this is one point that we know is on this line. And our tangent line here, you can see, is in red. And so, well, let's think about it. And we're talking about, we're looking for the equation of a line. And, well, we know a point on that line. Well, gosh, if we knew the slope of that line, then we could write the equation. So let's think about that for a second. And for that, we'll go over here to this part. So let's just recall. So let's look right here. So recall that the point slope form of a line, if we know a point on the line, that's what we call x1, y1. That's the point that we know. And in our particular example, that's -1, -1. So anyway, if we know the point, a point on the line, and we know the slope of the line, well, then we can just use this form of the equation of the line, which is the point slope formula, the point slope form. And that is what we're going to use a lot to work these kind of problems. And just so you know, problems like this, you know, where you're given an equation or given a function and a point on the curve of the graph, and, you know, finding the equation of the tangent line, that's a problem you're going to see over and over in this class. So if you're not familiar with, or if you need to, you know, review all the different forms of the equation of a line, in particular this form, then, you know, do that, because like I said, we will see that a lot. Okay, so let's use that form of the line to answer this question. So let's find the equation of this tangent line. All right, so now let's focus in on the part in the middle. So remember, we know the point -1, -1. So that's going to be our x1, y1 in that formula. And so to get the slope of the tangent line, that's where we use the derivative. So, you know, if you're thinking derivative, if you need to know the slope of the tangent line, think derivative, first derivative, because that's what tells us that. But you have to evaluate the first derivative at your x value. So that's what we need. So our m, our slope, or the slope of the tangent, we're going to get that by evaluating the first derivative, so our f prime, at -1. Okay, so at this point we need to recall that f prime of x is 3x squared. And so we're just going to evaluate that at -1, and so that's equal to 3 times -1 squared, which gives us 3. So the slope of the tangent line here is 3. So the slope, sorry about that. So the slope of that red line is 3. Now, if you just look at the picture, yeah, that kind of makes sense, because one thing that I tell my algebra students is, you know, if you look at a line, if you're looking at the graph of a line, Think about it as a road that you're traveling on from left to right. I know that's kind of silly, but if you're going up the hill from left to right, then that slope is positive. If you're going down the hill, if we were looking at a graph where the line goes, quote unquote, down the hill from left to right, then that would have a negative slope. That line would have a negative slope. And then, of course, a horizontal line, if you're traveling on a road that's exactly horizontal, from left to right, then that slope is 0. And then, of course, the last possibility is a vertical line. Well, you cannot drive, on a road that's vertical. So that's where you have slope that's undefined. But anyway, it makes perfect sense from this picture because that line's going up the hill from left to right, and it's pretty steep. So that slope of 3 here makes perfect sense. Okay, so now let's collect together what we know. We know the point and we know the slope. Okay, so now we just use the formula. So y minus y1 equals m times x minus x1. And that's it. There's your, that's the equation of the tangent line. And so you can just do a little bit of algebra. And you'll get this, y plus 1 is equal to 3 times x plus 1. And then if you do a little bit more algebra, you can get the equation y equal 3x plus 2. Now on the test, either one of these is fine. I don't really care unless the directions specifically ask for, a particular form of the line, then any one of these 3 would be fine. I just want to know that I just want it to be correct. So just to mention though, this last form is a very popular form. That's called the slope intercept form. You may remember that from algebra because the slope is that 3 setting right there. And the y-intercept the y-intercept is a point. It's 0, 2, and where does that 2 come from? Well, it comes from right there. And you can see that if you go back to the picture over here, you can see that tangent line is going to hit at 0, 2. Okay, so there's our first example. And so we'll pick back up with the next video in just a second.